In our last section, we talked about the concept of electric charge and how objects become charged. And at the last part of it, we were talking about electric fields and electric field strength. So what we're going to do today is we're going to continue on with that, and we're going to kind of go from the concept of static electricity into current electricity. But before we do that, there's a couple of concepts that we need to get out of the way. So just a quick review of those before we take a look at some questions from all publics that relate to those topics. So we're going to talk a little bit about the concept of electric potential. And you may recall from Physics 2204 that there was a topic there all about potential energy. And this is no different. Okay, when we talk about electric fields, there is still potential energy involved. So let's just take a quick look at that, and then we'll look at some actual questions from all publics. So, first of all, let's just briefly review the topic of equipotential lines. What you have to remember is it takes work to move a charge through an electric field. Because remember, if we have a positive test charge, and that's what we use to map an electric field, a positive test charge. So if we need to move that away from a negative source charge, remember the positive test charge and the negative source charge are attracting each other. So if we want to pull it away, we're going to have to exert a force. And if we exert a force and we move the object a distance, then by definition, we do work. And if we do work, we change the energy. So it's as simple as that. So at different distances away, because the field strength is changing as you move away from the object, there are different amounts of work needed. So what we're going to do is we're going to take a look at how much work would be needed to move at a certain distance through a field. Okay, and we're going to look at some formulas for that now in just a second. But what you need to remember is that if the field is uniform, like it is in this one down here. If this field is uniform, okay, you can see the field lines here, and you've got a bunch of lines pointing straight into the charge because you've got a negative main charge or source charge there. And to move a positive test charge from essentially the surface of the negative charge out to here, that requires a certain amount of work. But if you look at all around this dotted red line, to move it from the surface of the charge out to there is the same amount of work anywhere around that charge because that field is uniform around that charge. So what we call that is an equipotential line, or a line of equal potential energy. It takes the same amount of work to move from one place to the other. So from the surface of the charge out to this dotted red line is the same amount of work no matter where you are around that charge because it's a uniform field. So equipotential lines, kind of think of them like the layers of an onion. Okay, as you peel them off, okay, they get closer and closer and closer to the center. But when you have just a point charge like this, the equipotential lines are actually circles. However, when we go to a more irregularly shaped object, it becomes a little different because the electric field, if you look at the field lines, you'll notice that here at this pointy end, you'll notice that they're a lot closer together. That's because the charge tends to get concentrated at these pointy ends. So if the field is stronger here, that means the same amount of force is going to push that charge a much smaller distance. So if you see these dots here, these red dots, that shows you how far you can push the charge with a certain amount of force. Okay? In other words, that's the amount of work. To go from here to here is a certain amount of work. But over here on the end where the charge is much more concentrated and the field is stronger, you can go a much shorter distance and do the same amount of work. Okay? Because bigger force, smaller distance. So the same amount of work to go from here to here as there is from here to here. So you notice that the equipotential line is not a circle anymore. In fact, at the pointy ends, it's closer to the surface, and at the flat ends, it's farther away from the surface. So that's what we mean by equipotential lines. It's a line where anywhere on that line it would take the same amount of work to go from point A to point B. Okay? The easiest way to think of equipotential lines is just like contour lines on a map, and I'm sure you've come across those somewhere along the way. Contour lines on a map show elevation. And to go between two contour lines, that's the same elevation. Like, for example, over here, this is not very steep because you have to go a fairly long distance to get to that height. But over here, it's very steep because it's a much smaller distance to get to that height. It's harder to climb over here than it is right here. Now, you got to walk a longer distance here, but it's easier. Okay, less force required. Whereas over here, a lot of force, but a smaller distance. Okay, so that's very similar to the equipotential lines. They're just like contour lines on a map, so that's a really easy way to remember them. Anyway, let's talk about electric potential energy then. So electric potential energy is very similar to the concept of gravitational potential energy that you covered in Physics 2204. So the Earth, remember, is surrounded by a gravitational field. And that field is fairly uniform for the most part. And if we raise objects above the Earth's surface, we have to do work on them because we have to exert a force to move them a distance. So the work equals force times distance, or force because it's force of gravity would be mg, and the distance that you move it is h. So mgh, which coincidentally is also the same formula that we use to calculate gravitational potential energy. But anyway, when we raise an object above the Earth's surface to point A or point B, we increase its gravitational potential energy. But in order to do that, we have to do work on the object. We have to exert a force over a distance. And the work-energy theorem tells us that those two things are equal. The work that we do goes into increasing the energy. So work equals that change in energy. So we can actually develop a formula for that. Okay, and if you're lifting the box, say, from the ground to this height, and then from this height to here, well, on the ground it's 0. So work number 1 would be force of gravity times height 1, and work number 2 would be force of gravity times height 2. Or in other words, mgh and mgh. mgh1, mgh2. So essentially what we have here is the gravitational potential difference. In other words, the difference in gravitational potential energy would be mgh2 minus mgh1. Or, if we take the mg out as a common factor, we get mg h2 minus h1, or mg delta h. Now, the reason I'm showing you this is because it's a very close analogy to what happens with electric potential energy. Okay, so there's how we calculate the work done in a gravitational field. Right? The work equals change in energy, which is mg delta h. Let's look at electric fields now instead. If we apply that same reasoning to an electric field, then the same rules apply. Okay, we have to do work to move the object in the electric field because there's either an attraction or a repulsion between two charged objects, so we have to exert a force to move them, separate them, or push them together. So let's suppose we have a positive main charge that's surrounded by an electric field. And let's say we got a negative electron here that we're trying to move back and forth. So if we want to move this electron farther away, we have to exert a force on it to pull it away from the positive charge that it's being attracted to. So therefore, we have to do work on that. So that work is turned into electric potential energy. So at point 2, it has more electric potential energy than it has at point 1 because we had to do more work to move it there. In other words, we had to exert more force to move it a greater distance, etc., etc. So that is a difference in electric potential energy. So using the same reasoning we used before, and you may remember from our last topic that this was a formula for electric field strength. Electric field equals force divided by charge. So in other words, if we cross multiply and rearrange that formula, we get force equals charge times electric field strength. F equals QE. So what I can say then is force times distance. Okay, force times distance would be work. So work equals the change in energy, so it's force times distance. Or in other words, force times distance 1 minus distance 2. This expression right here. But force, remember, is Q times E. Because a lot of times when we're dealing with electric fields, the electric field strength is more useful to us than the actual force. So we replace the F with Q times E, and we get QE D2 minus D1, or QE delta D. Just like we had mg delta H for the magnetic, or for the gravitational field. It's a very, very similar idea. And because work equals energy, work energy theorem, here's a new formula for electric potential energy. Electric potential energy equals Q times E times D. And this E is the epsilon, which is field strength. This E over here, the printed E, that's energy. Capital E is what we always use for energy. So there's an expression for electric field strength, or electric potential energy based on the electric field strength, QED. Now this formula is not given to you on the public exam data sheet, but it would be a useful one to remember. You don't use it a whole lot. In fact, as I went back over the old public exams, it only showed up once or twice in the past 4 or 5 years. So, will you need it? Well, maybe, maybe not. Odds are probably not, but it's nice to know anyway. And it just comes from the whole idea of force times distance, right? Work equals force times distance. And the force is equal to Q times E. So it's an easy one to derive that way. So let's talk about then the difference between electric potential energy and electric potential, because they are two different terms. Okay, first of all, electric potential energy, which has the symbol EE, is the total amount of work done to move an electric charge in a field. So work equals energy, energy equals work. So because it's energy, the unit is joules. However, electric potential deals with only one unit of charge, 1 coulomb. So if we know how much charge is being moved, then we can come up with a formula for what we call electric potential. Now electric potential is better known as voltage. Okay? A lot of times we'll simply call that voltage. So electric potential, or V for voltage, is the electric potential energy per unit of charge. Okay, so it's not just the total energy, it's the total energy per unit of charge. So we take 1 unit of charge, 1 coulomb of charge, and move it through an electric field. So electric potential is the work done per unit of charge. So J over C, joules per coulomb, which we define as a volt. And it's calculated using this formula. V equals E over Q. Now that's another formula that's not given on the data sheet, but that's one I can pretty much guarantee you're going to need to know. So definitely remember that one. But if you remember the definition of electric potential, then you got it anyway. Sometimes we call it potential difference as well, which would be the difference in electric potential between 2 different points in an electric field. Okay, so that may come up every now and then, but distinction is not much different anyway. It's basically the same idea. So here's some formulas. Okay, here's the definition of electric field, F over Q. And if we, listen carefully, if we replace this F with the expression for Coulomb's law, it actually reduces down to this expression. Electric field equals KQ over R squared. And we did do that one in a previous class. Okay, then we have a couple of expressions for electric field. Okay, in other words, we take this, that QED that we just developed a minute ago, and we can substitute this expression, E equals KQ over R squared, for E right here. And if we do that, it reduces down to this guy right here, KQ1, Q2 over R. You notice the difference in Coulomb's law on this one is the R is not squared. That's the only difference. And then there's two expressions for V as well. V, we just said a moment ago, was E over Q. That's the definition of electric potential or voltage. And then by substituting this expression right here for E right here, we get another expression for V. So we've actually got two expressions for each of these variables. And now that means you actually have four equations that have K, Q, and R in it. Four different equations. There's Coulomb's law, which is KQ1, Q2 over R squared. There's electric field strength, which is KQ over R squared. Those two, by the way, are on the data sheet. They are on the physics formula sheet. Okay, these other two are not. So those two you're going to need to remember. You may need them, you may not. Lots of times you can do it by doing this first and then possibly doing this. Okay, so there's all kinds of ways around that, but it would be very helpful to memorize or at least remember how to derive those other formulas. So there are some formulas, in other words, that are not given on the data sheet that may come in handy. Do you absolutely have to memorize them? Probably not. But it would speed things up sometimes in a number of different questions. All right, so let's take a look at some public exam questions that deal with that particular concept, that deal with the concept of electric potential and electric potential energy. Remember, two different things. Okay, mostly multiple choice for this stuff. So we got, in the first one here, work required to move an electric charge between 2 points in a field is 0.0045 joules. If the potential difference, or electric potential, like I said, potential difference is a lot of times used in that place, but it essentially means the same thing. The potential difference is the difference in electric potential between 2 points. Okay, but we use it exactly the same way. What amount of charge must have been moved? Well, the formula we know for electric potential is V is equal to E over Q. V equals E over Q. Like I said, remember that formula. It's going to come in very useful. I can pretty much guarantee you're going to need that one. So that would be a good one to know, because that's the definition of electric field, or electric potential anyway. Now we're trying to find Q. So I'm going to rearrange that formula now. And all I got to do to rearrange it is swap the Q and the V. So Q equals E, energy, over V, which is electric potential. Now the energy is the same as work. Remember, work and energy can be used interchangeably in these problems. So the energy is given 0.0045, and the electric potential or potential difference is given 12 volts. And you do that calculation, here's what you get. 3.75 times 10 to the power of -4. Now, that's one of the answers there. When we round it off to 2 sig figs, it's this one right here. Then we move on to the next one. Now the next one would be more of a level 3 question. Okay, this is a multi-step. You have to do two things in this one. Because remember now, in order to find E, there's different ways to do it, but based on the information you're given, in order to find E, you're going to need to know Q. So the first thing we got to do is we got to find Q. Well, remember the definition for electric field strength. E equals F over Q. So what I'm going to do is I'm going to rearrange that for Q, and Q would equal F over E. In other words, force divided by field strength. And we do know both of those values. So that will tell us how much charge is being moved through the field. And it's 0.5 coulombs, half a coulomb. Now we can do this. Now we can say V equals E over Q, which means in order to find the work or the energy, all I got to do is rewrite this equation. I'm going to cross multiply and I'll find E equals V times Q. So the V, the potential difference here, or the voltage, is 450 volts. The Q we just found is 0.5. Multiply those, and the answer is 225, and that's joules. Now that rounds off to 2.3 times 10 to the power of 2. That many joules of work, which is the same thing as energy, right? Work and energy, like I said, in these questions, we use it interchangeably. Okay, potential difference across a battery is 6 volts. How much work is done? Well, exactly what we just did. E equals V times Q, right? E equals V times Q. There's V, there's Q. Multiply them together, you get 3,600 joules. And that's written here as 3.6 times 10 to the power of 3, or D. Okay, the next one, how much work is done by this power supply, in other words, this voltage, 9.00 volts, moving this many electrons. So this one, there's an extra step. Remember this formula. If you want to find charge and you know the number of electrons, you can say Q equals N times E. In other words, 8.50 times 10 to the power of 18 multiplied by the charge on one electron, which is 1.60 times 10 to the negative 19. And the answer to that is 1.36 coulombs. Now we can do it the same way we just did it in the previous question. E equals V times Q. Okay, we know the Q, we know the V because they're given, and you multiply those two numbers together, you get this answer, 12.24 joules, which is this in scientific notation. Now you'll notice that you really need to know your scientific notation, so if you're having trouble with that, you better go back and take a look at it, because that's going to be a skill that you're going to need for the public exam, I can guarantee it, because a lot of times the answers are given in scientific notation. The last one here on this page is a definition. The work required to move a charge from one point to another in an electric field. That is the electric potential energy right here. Technically, that should be electric potential energy. Okay, I'd argue that one because that's technically not correct. That should say energy. If it was the work per unit of charge, then it would be electric potential, but it doesn't specifically say that, so that would actually be the correct answer. All right, a couple more. Very simply, amount of energy gained by a proton. Well, even though we're not given a charge, we know the charge because it says a proton. E equals V times Q. Okay, 1 volt times the charge on a proton. Well, the charge on a proton is exactly the same as a charge on an electron, which is given on the data sheet. 1.60 times 10 to the negative 19 times 1 is 1.6 times 10 to the negative 19. That's a pretty simple one. Okay, and the last one, definition, V equals E over Q. We're given the E because we're given work, right? Work and energy, same thing. So we know the energy, and because it's an electron, we know the charge. All we have to do is divide. And when you divide those two numbers, the 4.8 times 10 to the negative 17, divided by the charge on an electron, which is this, straight off the data sheet, the answer there is 300 volts. But it's not written like that in the answers. Again, they're using scientific notation, which is 3 times 10 to the 2. The answer is C. Okay, so those are the types of questions you can expect to see about electric potential energy and electric potential. So what we're going to do in our next session is we're going to go on and we're going to take a look at the difference between electric current and voltage. Okay, now we've already introduced voltage, so we're going to take it a step further now in the next section. But we're also going to introduce the concept of current. In other words, moving electrons, moving charge. Okay, so good luck with your exam. Study hard, and don't forget to come back and take a look at some of these other topics to make sure that you know them.